Hi, welcome to the 8th session on group theory. The topic of today's lecture will be subgroups. We will start with the most useful definition of a subgroup, slightly different from the textbooks, but it's the most useful. Then we will also look at a lot of examples. Okay. And we'll also try to prove some basic results about subgroups which may be useful later. So let us get started. So as usual, you can download the list of videos from my channel from this page. Okay. Right, let's get started. So let us start with an example. Suppose let us look at the group Z under addition, that is additive group of integers. Let me just make sure that recording is on. Yeah, right. Now let us look at even integers, 2 times Z, that is even integers, multiples of 2, right. Now you can see 0 belong to this. Let H be equal to this and G be equal to this. Then 0 belong to H. And whenever I have M and N in H, then M plus N is also in H. Because M and N are even integers, therefore it's of the form 2K and 2L. Their sum will be 2 times K plus L. That's also an even integer. And similarly, for every M in H, which is let us say 2K minus M equal to 2 times minus K, that is also in H. Right? So these are the three properties. Whenever 0 is in H, whenever X and Y are in H, X plus Y is in H, and whenever X is in H, its inverse is also in H. Right? So this is what we want to abstract. So let us start with the definition. Let G be a group. Okay. Remember G, when I say, it will be with this. The binary operation is dot. X dot Y we may write as only XY rather than X dot Y. Okay. And H be a subset of G. Okay. With the following property. Yes. Okay. A subgroup or a subset H of G H of G is a subgroup of G if the following conditions are satisfied. Namely, the identity element of G is an element of H, where E is the identity element of G, and that should be in H. 2. Whenever A and B are in H, A dot B, that is AB, that should also be in H. The third condition, this is for all A. This is for every A in H, the inverse, A inverse is also in H. Okay. You understand this definition? So notice that by our definition, if H is a subgroup, it is non-empty because we know E has to be in G. E has to be in H. Right? Because most of the textbook will say a non-empty subset and they insist only on 2 and 3. Let's not worry about this, is the best definition. So whenever you are given a group, okay, and a subset H, you want to prove H is a subgroup, the first thing you should check is whether identity elements is in H. The second thing you should check is take any two arbitrary elements of H, then the binary product AB, whether it is in H. The third thing you have to check is start with any element A, arbitrary element A in H, its inverse should be in H. Is that clear? So pause, review, proceed. Okay. So now let's look at examples. So as we did, let G be the group under addition, or the additive group of integers. Then fix an N in Z. Okay. Let Hn be equal to N times Z. That is all multiples of N. Right. Then notice that 0 has to be there. What does n stands for? Let us look at that. Nz by definition it is, okay, n times n, where m varies over integers, all integers, right? Okay. Now notice that when I take m equal to 0, then n times 0 is 0, therefore 0 is an n, nz, which is hn. The first condition is satisfied. What is the second condition? Let a and b be in hn, that means a is some k times n and b is some l times n, then a plus b is k plus n times n. Therefore, that's also in hn. This is exactly the way we check for even integers, right? If a is in hn and a is kn, then what is minus a? The additive inverse. Additive inverse is minus kn, but I can write it as minus k times n. And remember, k is an integer, therefore this again belongs to hn, right? Are you following? Right. In particular, easier thing will be, suppose I take n equal to 2 and or n equal to minus 2. Is there any difference between hn? Okay, call it h2, call it h minus 2. Okay, is there any difference? They are the same, because all multiples of 2, all integral multiples, right? Suppose I say minus 10 is there, but minus 10 will be there as here minus 5 times 2. Here it will be 5 times minus 2. You understand this? Are you following? Because any element, if a is in h2, okay, that means a is of the form k times 2, right? But that is also in minus 2, because it's minus k times minus 2. Therefore, it is in h of minus 2. Are you following? This is minus k times minus 2. This is also an integer, therefore its integral multiple of minus 2, therefore this is h minus 2. And conversely, therefore we see h2 is same as h of minus 2. Therefore, what is the lesson we learned? That is, for every non-negative integers, that is n is in z and n is greater than or equal to 0, this hn is defined. This is all multiples of n. Okay, that's good enough. I don't have to consider n to be negative. Are you following? Because hn is same as h of minus n. So pause, review, proceed. Right? Now, next question is, if I give you some n and let us say r, n is not equal to r, and n and r in z plus, what is the relation between hn and hr? Are they same? Yeah. So without loss of generality, I can assume my r is less than n, 0 less than or equal to n, right? They are distinct, therefore I can assume this, right? Therefore r belongs to hr, but r cannot be in hn. Why? If r has to be in hn, it must be a multiple of n. That means it must belong to 0, n, 2n, or minus n, etc. I am assuming r is positive, therefore it has to be one of them, right? Any element which is here, okay, it will be multiple of n, therefore 0, n, or 2n, but r is strictly less than n. Therefore, what I have seen is hr and hn are distinct. They are not the same sets. Have you understood? Okay. Next, I'm just playing with this. The next thing is, suppose I have n and d is a divisor of n. Okay. Of course, assume that n is in z plus and d is a natural number that divides n. Then I have hn and hd. What is the relation? Notice that when n d divides n means n is a multiple of d. Therefore, m belongs to hd, right? And therefore, you give me any k times n, any element a in hn, then a is of the form k times n, but that is k times m times d, and therefore it is in hd. Therefore, what you have shown is hn is contained in hd. So these are the examples. Usually it's never looked at in standard courses. I hope you understand this thing, right? Please review. We will go to extra examples now. Okay, but I wanted to teach you how to look for this. Okay, how to use the definition. When I want to say something is not as a group or not as a group, how to do that? Okay, some non-trivial example will help you. Okay, let us do that. Now let us look at one example. Remember GTL2R? This is 2 cross 2 invertible matrices. Okay, therefore a matrix A in M2R, that is 2 by 2 real matrix, that belongs to GL2R. This is my G. It belongs to G if and only if determinant of G is, determinant of A is non-zero. We had seen all these things. Okay, right. Now let me look at this H, the set of all elements, okay, of the form A, B, 0, A in GL2R. So the obvious condition is A cannot be 0 because determinant is going to be A squared, right? Therefore A is not 0, and there is no condition on B. B is any real number. So A and B are all right. So this H is a subset of G, right? What is that I have to check? It is a subset of G. I have to make sure it is invertible. So when is it invertible? If and only if the determinant is non-zero. What is the determinant? A squared. Since A is non-zero, okay, determinant of any element here is non-zero, and hence it's H is a subset of G. Is that clear? Okay. Does identity belong to this identity matrix? Identity matrix 1 0 0 1. So if you give me a matrix, let us say something like X Y Z W, when does it belong to? Suppose this belongs to GL2R. Okay, assume this belongs to GL2R. When does it belong to H? This is what you have to learn. If you have gone through foundation course, you will understand this thing. This means it must be of this form. That means my X and W must be the same, right? And Z must be 0. That's it. These are the only conditions. Do you understand this? So if I want to show some element of GL2R, namely X, Y, Z, W, if it belongs to H, what is that I have to check? I have to make sure the diagonal elements are identical or the same. X equal to W. And this element, okay, A to 1, that element must be 0. Okay, are you following? Good. So therefore this belongs to H because A equal to, the diagonal elements are the same, this element is 0, therefore it belongs to H, right? Now start with two elements here. Okay, let us say A, B, 0, A, and the next one is, let us say, alpha, beta, 0, alpha. Both are in H. Okay, then I want to know whether it is in H. So let us do the multiplication. A alpha, B0, therefore A alpha, and A beta plus B alpha, and 0 times alpha plus A times 0, 0, 0 times beta, 0 times beta, this is A alpha. You understand this? Now since both these elements are in H, A is non-zero and alpha is non-zero. Therefore A alpha is non-zero. And diagonal elements are the same and this element is 0. Therefore this is an element of H. right? So we have verified two conditions. Identity element belong to H. Product of two elements in H is an element of H. Okay, right. And what is the third condition? Third condition is the inverse. You start with an element A, B, A in H, and I have to check whether its inverse belong to H. Okay, this is what I have to check. Right? Now, how do I check it? Let us recall. All of you must have learned even in higher secondary. If I have A, B, C, D, assume determinant is AD minus BC is non-zero because I am assuming it's invertible. This is an element of GL2R. Right? So call it as A. What is A inverse? A inverse is 1 by the determinant, that is AD minus BC, into D A minus B minus C. Yeah, I hope I am right. AD minus BC, correct, and A minus BA, BA 0, and CD is 0, and minus BC, yeah, right. This is the inverse, right? Now to start with the element in H, this is already in invertible, right? Therefore, what is the inverse? What is the determinant? Determinant is A squared. Therefore, if A is A B 0, A inverse is determinant 1 by A squared into D is also A, right, and B, you write minus B, and Z is minus 0, which is 0, and then write A. This is the same as A inverse minus B 0 A inverse. Remember, A inverse stands for the reciprocal 1 by A. Yeah. Now, since A is non-zero, this is non-zero, this is non-zero, this element is 0, this is an element of H. Right? So, we have proved H is a subgroup of GL2R. Whenever H is a subgroup, I usually denote it by H less than or equal to G because there is a structure. Okay, this is just a meaning. I read it as H is a subgroup of G. So, go through this example. You understand, I took one. Usually, these kind of exams are not done because many students may not even know what they have to check. Okay, that's why I took this example. So, how to identify an element in the group to be in the subset. That's the first condition we learn, and then we have to check whether the subset is a subgroup. These three conditions we checked. Okay, we go through it. So if you are the first time learning these things, you will appreciate this. Okay, right. So let's go to the other examples. So some of the standard examples I will see. Okay, suppose G is a group. Then let us look at H only consisting of the identity element and H equal to all of G. These are subgroups of G. Why? Identity element belong to this H, call it H. Okay, H0, H full. Okay, right? E belong to this, E belong to this. Next, take any two elements, there is only E, therefore E times E, that belong to H. And take any element H naught, which is E, its inverse is itself. You understand that? Yeah, E belong to H naught, E inverse is E. Therefore, okay, the H is a subgroup. H naught is a subgroup. Is that clear? Now this requires nothing, right? Because this is a G is a group, therefore take any two elements A and B, yet A dot B has to be in G. Since G is a group, if A is an element of G, then A inverse the inverse exists, that is A inverse that belong to G. These are called trivial subgroups. So whatever be the group, we already have two groups, subgroups. Is that clear? Okay. The next thing, let me just make sure I'm sharing. Yes. Okay. The next thing I want to do is, let's look at, we looked at only additive groups so far. Let's look at, of course, matrix is not additive group. Let us look at some of our standard examples. Suppose look at symmetry group of on. Let an be the set of elements sigma in Sn, so that sine of sigma is 1. Then I claim an is a subgroup of Sn. Why? Identity permutation. Okay, that is an an because sine of identity is 1. Next, whenever sigma and tau are in an, okay, that means sine of sigma is 1, sine of tau is 1, then I would look at sine of sigma tau. Notice that when we define about the sign of a permutation, we saw that it is sine of sigma tau is sine of sigma times sine of tau. But each is 1, 1.1 is 1. Therefore, this implies sigma tau is in an. Yeah. The third thing, suppose sigma is in an, and I would look at sigma inverse, whether it is in an. Right? But again, we can do this easy trick. Let us look at sine of sigma inverse. That is going to be, this is sine of identity, that is equal to 1, and this is going to be sine of sigma into sine of sigma inverse, right? But this is 1. So 1 dot, this is either plus 1 or minus 1, but the product is equal to 1. Therefore, we conclude sine of sigma inverse is 1. Therefore, an is a subgroup of Sn. This is called alternating subgroup. Okay, P or P. Very similar to that is the next example. Let us look at GL2R, maybe GLNR also. This is my group. Okay, this is under matrix multiplication. These are all set of n by n invertible matrices. Right? Right. Now identity element, let us look at H to be A in G, so the determinant of A equal to 1. Right? If A belong to this, determinant is non-zero, but I want to look at only those elements whose determinant is 1. Now identity I equal to n cross n, this belongs to H. Because identity of G is identity matrix that belongs to H, because determinant of identity is 1. Identity matrix is 1. Next, let A and B belong to H. Then I have to say whether A, B belong to H. But what is the condition to check whether A, B belong to H? I have to make sure what is determinant of A, B, whether it is equal to 1. I have to check this. But remember, determinant is multiplicative. That means determinant of the product is the product of the determinants. And I know this is 1, this is 1, because A and B belong to this, therefore the product is 1. Right? The next thing I have to prove is A belong to H. Does it imply A inverse belong to H? What does that mean? That means I have to check whether the determinant of A inverse is 1. This is what I have to check. But how do you think I will approach? How will I prove that? Exactly the same way we proved sine. That is, look at determinant of A times A inverse. That is determinant of identities is 1. But determinant of A times A inverse is determinant of A times determinant of A inverse. But determinant of A is 1. Therefore, we conclude determinant of A inverse is also 1. Is that clear? I don't want to write it. Did you follow this? Okay. So, determinant of A into determinant of A inverse. This is equal to 1 into determinant of A inverse. Okay. Notice that since A belongs to H, this is invertible. A inverse also belongs to the, therefore it is in G and right? Therefore, determinant of A inverse is non-zero. Okay. That into 1 equal to 1. Therefore, this must be equal to 1. So, we proved H is a subgroup. This group is known as special linear group. SPECIAL. SLNR. The last one, this GLNR is called general linear group. Okay. P R P. Now let's look at something slightly easier also. Now let's look at R star, that is non-zero reals under multiplication. We know it's a group. It's also an abelian group, right? Right. Now let's look at the set which is plus or minus 1. What is the identity element of this group? Identity element is the number 1, right? Therefore, H is an R star, right? And 1 belongs to H. Now take any two elements here and their product. 1 times 1 is 1, minus 1 times minus 1 is 1, plus 1 times minus 1 is minus 1, minus 1 times plus 1 is 1. Therefore, this, okay, second condition is also satisfied. If A and B belong to H, A times B also belong to H. That is also checked. Now, what is the third one? If A belong to H, either A is 1, in that case A inverse is 1, that belong to H. If A equal to minus 1, in that case A inverse is again minus 1, that belong to H. Right? And there are only two elements. Therefore, H is a subgroup of R star. Right? Okay. But so under multiplication, I looked at, see now R star is an infinite group. That is, it's not a finite group. But this is a finite subgroup. H is a finite subgroup of an infinite group. We can generalize this example. Suppose my G is C star, non-zero complex numbers, okay, under multiplication. Right? Then we know this is the group and one is the identity. Okay, this is a group. It's an abelian group. Right? Now, let us look at first, say, let us look at the simplest one. Here also, if I take H, call it H2 equal to plus or minus 1, this is the subgroup of C star, exactly as we saw earlier. Now, let us look at H4. This is plus or minus 1 and plus or minus I. What is I? I is one of the square roots of minus 1. Okay. There are two square roots, plus or minus 1. This is minus 1. Okay. Now they also form a group, right? 1 and minus 1 I have done, and if I multiply 1 by plus I, I will get plus I, 1 by minus I will get minus I, minus 1 by plus I will get minus I, and minus 1 by times minus I will be plus I, and so on. Therefore, okay, that. And what is the inverse? See, if I have I, what is I inverse? I inverse is 1 by I, that is equal to minus 1 times minus 1 by I, that is minus 1 times I squared by I, but that is minus I. You understand this? Right? Therefore, similarly, minus I inverse will be I. Okay, Are you following? Because I times minus I is minus I squared, which is minus of minus 1, which is plus 1. So this is a subgroup. H4 is also a subgroup of C star. Notice that both are finite groups, finite subgroups, right? Are you curious? Why did I denote those groups by H2, H4, etc.? Does that mean for each power of 2 I can have a subgroup? Much more. For every natural number n, I can look at the nth roots of unity. I'm sure in your higher secondary you would have learned nth roots of unity in a complex number system, right? So they form a group. They form a subgroup. Okay. And so please go through it. If you want, I will write it. Let us see. So more generally, fix natural number n. Okay, assume that n is greater than or equal to 2 or to avoid, right? Let let omega be a nth root of unity. That is omega power n. So let omega be e power 2 pi I by n, which is in terms of cos 2 pi by n plus I times sine 2 pi by n. Remember, I am using Euler's formula, De Moivre's theorem. Okay, it's easier to use this rather than trigonometric function, but whatever it is, right? Now, if you look at Hn to be 1 omega squared up to omega power n minus 1, and omega power n will be 1. Okay, so this is known as a primitive nth root of unity. This is primitive, primitive primitive nth root of. They form a group. Okay, how do I do this? I'm going to say Hn. That what does it mean? You start with an element omega power r and omega power s, then I have to show that belong to Hn. Right? Take omega power r, omega power s here. I have to say this belong to Hn. Right? Are you following? Yeah? Okay. But there is that can be done. This what is this? This is omega power r plus s. Now r plus s may be greater than or equal to n, therefore I can write it as some n times some. This r and r are bad, so let me take kl. Okay, k plus l. Remember 0 less than or equal to k less than n minus 1, and l also 0 less than or equal to l less than n minus 1. Therefore k plus l will be less than 2n minus 2. Therefore it will be less than 2n. Right? Therefore k plus l I can write as some n times r by division algorithm. Right? 1n, it cannot be 2 times n. You understand that? Yeah? Right? Therefore, omega power k power l is same as omega power n into omega power r, but omega power n is 1, therefore it is omega to the power r. Where is r? R will be 0 less than or equal to r less than n minus 1. Therefore, it belongs to H. See, I forgot to screen share. This is what happens. Okay, let me screen share. So what we do is, for each natural number n greater than or equal to 2, we will define a primitive nth root of unity by omega equal to e power 2 pi I by n. Right? Okay. I hope that all of you have learned in 12th standard. Okay. Then this is same as in using Euler's identity. This is cos of 2 pi by n plus I times sine of 2 pi by n. Okay. You can use De Moivre's theorem. Right. Now what are the elements Hn? The elements are 1 omega squared omega to the power n minus 1. Okay, yes. Right. Now I want to say, now notice that 1 belong to this. The next thing what I want to show, I want to show the product of two elements from here. They are again an element of Hn. Right. So one element is take omega power k and another one omega power L. Therefore the product is omega power k plus L. Right. But k plus L may overshoot n. It may not be here, right? Suppose my n equal to 5 and my k equal to 3 and L equal to 4, then k plus L, this will be 7. Then what do? I divide it by 5, and that's what I did. Notice that 0 is less than or equal to k, strictly less than n minus 1. 0 is less than or equal to L, strictly less than n minus 1. Therefore, k plus L will be non-negative, but it will be strictly less than 2n minus 2, right? Therefore, when I divide by n by division algorithm, what I will get is k plus L plus n, and there is a remainder r. This remainder has to be between 0 less than or equal to r less than n minus 1. And omega power k plus L is omega power n times omega power r. Omega power n is 1, therefore it's omega power r, therefore that belongs to this. Okay. So we proved 1 belong to Hn, and if omega k, omega L belong to Hn, omega power k plus L belong to Hn. Okay. The third, omega power minus k. Omega power k belong to Hn, and omega power k to the power minus 1. Does it belong to Hn? So I should know what is omega. It's inverse. Okay. That is very easy, because notice that 0 less than or equal to k less than n, strictly less than n, right? Therefore, if I take L equal to n minus k, right? See, notice that 0 greater than or equal to minus k greater than or equal to minus n. You understand that? 0 less than k less than n. Okay. Now, what can I say about n minus k? That will also be 0 less than or equal to L less than n. Okay. Sorry. Can be n, because if k equal to 0, my L will be n. Okay. So let us assume this is less than 1. If k equal to 0, then omega power 0 is 1. Therefore, its inverse is 1 inverse is 1, that belong to Hn. So let us assume my k is 1 less than or equal to k less than n. Okay. Now let us look at L equal to n minus k. Then you can see this is going to be 1 less than or equal to L less than n, or strictly less than n. Am I clear? Now what is omega power k into omega power L? It is omega power k into omega power n minus k, that is omega power n, which is 1. Therefore, omega power L is equal to omega power k at its inverse. To make sure omega power L belong to Hn, I have to make sure my L is less than n. That's what we just now did. Yeah, it has to be 0 less than or equal to L, but that we already took care, therefore it must be strictly less than n. Pause, review, proceed. Please make sure you understood the last argument. Okay. I will look at omega power k. If k equal to 0, it is 1, and its inverse is itself. Therefore, no question. Therefore, I can assume omega power k is 1 less than or equal to k, strictly less than n. Then I have to say its inverse. I claim the inverse is, yeah, omega to the power n minus k. Right? Okay. You prove it. Then what do I know? What happens to n minus k? Now remember, k is greater than or equal to 1. Therefore, n minus k will be strictly less than n. That's it. Is that clear? So we proved the nth roots of unity. Okay. These are, they form a subgroup. In fact, I just slid over a small subtle point. I will mention that in a minute. So the way I define Hn is look at a primitive nth root of unity, then listed all elements, right? But there is another description. This description is look at the set of elements Z in C, so that Z power n equal to identity. Okay, and this is what you must have seen in your higher secondary. These two sets are the same. Okay, to write this, what you do is you look at one primitive nth root of unity and all roots are, look at this, Z power n equal to 1. Okay, this is a nth degree polynomial, therefore it will have n roots. Okay, and all these fellows are roots, right? So this will have n elements. Okay, this set will have n elements, right? And this set also has n elements. We have to check why they have n elements. I'll come to that in a minute. Okay, yeah, and all of them, am I going fast? See, Hn we already defined. Now Hn has an alternate description, namely set of complex numbers such that nth power equal to 1. Okay, now I want to say these two sets are the same. Okay, the first thing I want to say is start with n element here. Okay, omega power k, then I want to say it belongs to this. Okay, it belongs to this. Maybe I'll call it Hn dash. Okay, it belongs to Hn dash. For an element complex number to belong to Hn dash, what do I have to check? Its power n should be equal to 1. But that is clear because it is omega power kn. But omega power kn is same as omega power n times k. That is 1 power k, which is 1. Right? Therefore, I have shown Hn is contained in Hn dash. Right? Now remember, Hn dash has n elements because it is the roots of the nth degree polynomial. Therefore, there are at most n roots. Okay, at most n roots. Okay, I do so. Hn dash will be less than or equal to n. Are you following? Yeah. Now I claim Hn is already contained Hn dash, and I will show Hn has exactly n elements. How do I know that? Because let us look at omega power k. Suppose omega power l, k is not equal to l, and 0 less than or equal to k, l less than, strictly less than n. Right? With our loss of generality, let me assume k is less than l. Then this means omega power l minus k, okay, equal to 1. Right? Multiply both sides by omega power minus k. Yeah, that is equal to 1. Right? Now notice that 0 less than or equal to l minus k, strictly less than n. Right? But none of these elements, okay, if you want to call it as, yes, this omega power s 0 less than, yes, less than or equal to s less than n, omega power s equal to 1. Okay. And in this, you can see except when s equal to 0, this you can't call it omega power 0, omega power 1, omega power n minus 1. The only element which is equal to 0, equal to 1 is when the power of omega is 0. That means L minus k must be 0. That means L equal to k. Right? So what is that I have shown? I have shown that among these these elements, if k is different from L, omega power k is different from omega power L. This is what I have proved. So we conclude, if k is not equal to L, 0 less than or equal to k, L less than n, then omega power k is distinct from omega power L. Therefore, mod Hn is n, and Hn is contained in Hn dash. We know Hn dash less than or equal to n. Therefore, what is the conclusion? Hn equal to Hn dash. Hn is a subset of Hn dash, but Hn has n elements, Hn dash has at most n elements. That means the sets Hn and Hn dash are the same. Okay, I hope it's not overwhelming. This is one of the worst, because after higher secondary you may not have looked at complex numbers very carefully, nth roots of unity, etc. So it's time to review this, then you will understand this example. Okay, is that clear? So for each n natural number greater than or equal to 1, because n equal to 1, it's a 1th root of unity, that means only 1. Okay, h2 is plus or minus 1, that is square roots of unity, and h4 is all 4th roots of unity, that is plus or minus 1 plus or minus I. In general, for any n natural number we define hn. They are called nth roots of unity and they form a subgroup under multiplication. Is that clear to you? Very good. Okay, now we will do something more. Let me see what kind of example I can think of before that. Yeah, let us try to think of an abstract example, one more abstract example before I close. Okay, we will continue this study of subgroups later also, but I want to think of an abstract example. Okay, let us do that. So let G be a group. Okay, fix an element A in G. Let us look at this subset H, which is all G in G, such that AG equal to GA. Notice that H is a group, therefore it may not be commutative. So if you give an element A and give me an element G, AG may not be equal to GA. But what do? I look at only those elements, okay, which commute with A. That is, this is the set of all elements in G that commute with A. I want to know whether H is a subgroup. Subgroup of G. Right? So what are the things I have to check? I have to check first thing is whether E belongs to H. Right? I think I have not changed my color of the pen. So let me do that. Okay, the first question is, does E belong to H? But that's clear. When does E, an element belong to H? If and only if it commutes with A. That means I want to know whether AE is same as EA. But since E is an identity element, this is also A, this is also A. Therefore, this is correct. Next thing, let me say G and H belong to H. Then I want to know whether GH belong to H. Yeah. So when does GH belong to H? If only if, that is, this happens if only if GH times A must be A times GH. I interchange the way, it's okay. Is that clear? I am asking whether these are the same. If it happens, then GH belongs to H. Right? But what do you think we will do? I can use associative law. This fellow is the same as G into HA. And this fellow is AG into H. Is it okay? Right. Now H belongs to little h belong to H, therefore HA is same as G times AH. And this fellow similarly is same as G times A times H. Right? Now I can use associative law, therefore it is GA times H, and this is G times AH. Right? Now again I use associative law, this is C times AH. This is okay. G times, I hope I wrote it correctly. Yeah, okay. G times AH. Right? This is G times AH is okay. Now since H belong to capital H, this is HA. Associative law I can use, this is GHA. Right? And what is this? Here H belong to A, therefore this is G times HA, therefore GHA. So both, so GHA is same as AGH. So I need not have done this at all. Okay. So it's enough if we can focus only on AGH. AGH by associative law it's AGH, and since G belong to H, therefore it is GAH, but this is equal to associative law G to AH, and since H belong to capital H, this is G times HA, but associative law it is GHA. But that's what we started with. Okay, we proved this right side equal to the left side, so I did not have done this. No need. Is that clear? So what have we shown? We have shown that whenever G and H belong to H, GH belong to H. That means G commutes with A, H commutes with A, then GH also commutes with A. Right? The last one, suppose G belong to H, then I ought to know whether G inverse belong to H. Right? Okay. When does it happen? This happens if only if G inverse A must be equal to A G inverse. That is G inverse commutes with A. Right? Let us start with this. Since G belong to H, that means GA equal to AG. Right? So I multiply this by G inverse on both sides. Therefore G inverse GA equal to G inverse AG. Right? Multiplying by both by C on the left by G inverse. But using associativity, etc. Okay, this is G inverse G, which is A. Therefore this is A. Left side is A, the right side is G inverse A G. Right? Now I want to get rid of this G on the right side, so multiply both sides on the right by G inverse. This is A inverse G, this is G inverse A G into G inverse. So I am using associative law, so I don't spell it out. But G inverse is the identity, therefore it is G inverse A. Therefore I have proved A G inverse equal to G inverse A. That means G inverse also belong to H. Okay. Therefore H is a subgroup of G. This H is usually denoted by CG of A. This is the centralizer subgroup of A in G. That is set of elements that commute with the A. So you can see in the last example is abstract. Okay, there is no concrete group anything, but we did that. There is some interesting question I can ask in this. Suppose my A happens to be identity. What is the centralized subgroup of A? That is the set of elements G which commutes with E. That I know. Each and every element of G commutes with E. Therefore, centralizer of E in G is G itself. I get the full subgroup. Are you following? Okay, I'll just close it with a little abstract example. Okay, special cases. Suppose A is G, then CG of E is G itself, because all elements in G commute to E. Is that clear? Right. Now this tells me something more. Suppose A has the property A commutes with each and every element. Then also CA of G is G. right? Yeah, right. So this kind of elements have a special name. Center of G, one usually denoted by that of G, is set of A in G, so that AG equal to GA for all G in G. So collect all elements that commute with each and every element. You understand that? There is a subtle difference. Here I took A to be an element which commutes with all elements of G. Then I proved CA of G is G. Here I am look at all elements which commute with each and every element. Right? So I want to say ZG is also a subgroup of G. Again, start. If E belong to Z, does it belong to that? Right. Because when does some element belong to ZG, the center of G, it should commute to each and every element of G. Does identity element do that? Yes. Therefore, this is correct. Next, suppose, okay, G, H belong to Z of G. Then what is that I have to do? Okay, or maybe A and B. Suppose A and B belong to Z of G. Then I want to say A, B belong to Z of G. How do I do that? The only way is start with any arbitrary element G in G. I have to check whether A, B, G is same as G times AB, whether this element commutes with G, right? But using associativity, this fellow is A times BG, right? Since B commutes with each and every element of G, this is same as A times GB. By associativity, this is same as AG times B. But again, A commutes with each and every element, therefore this is same as GA B. But using associativity, it is G times AB. So you have proved this fellow is equal to this fellow. Right? Therefore, what I have shown? I have shown that if A and B are in the center of G, then the product is also in the center of G. Now the last element is if A is in center of G, whether A inverse belong to center of G. That again is exactly the same way we proved earlier, right? So start with any arbitrary element G in G. That means I want to check A inverse G whether it's equal to G A inverse, right? There are many ways of doing. Okay, let me do that. I know AG equal to GA, right? Therefore, multiply both sides by G inverse AG equal to G inverse GA. I have to put bracket. I am using associativity, so I will not bother. This is equal to A, right? Now multiply both sides by on the right by G inverse AG, G inverse equal to AG inverse. This is identity. Therefore, AG inverse A equal to AG inverse, right? Therefore, G inverse commute, so A commutes with G inverse for each every G. Okay, A inverse commutes with each and every G, right? That is A inverse commutes with every G in G. That means A inverse belong to center of G. Therefore, we have proved center of G is a subgroup of G. Oh my gosh. So, okay, I have to stop with this. So let us look at what I did. So I want to define center of G equal to set of all elements A in G so that A commutes with each and every element of G. You understand that? Okay. Now I want to say this is a subgroup. So what do I the thing I have to check? Whether E is in center of G. That means I have to check whether E commutes with each and every element of G. That is correct. Therefore this is correct. The next thing is start with A and B which are in the center. That means A and B commute with each and every G, an element G. then I want to say whether the product is in ZG. How did I do that? That means I have to check, start with any arbitrary element G in G. I have to make sure AB commutes with G. That means AB times G is same as G times AB. So let us look at the left side, work out by associativity, this is A times BG, right? But since B commutes with each and every element, BG is same as GB, right? Now again use associativity, this is AG times B, right? But this again you can say, since A commutes with each and every G, this is GA times B. But use again associativity G times AB, so which is the right side, right? And the same way, when A belong to the center, I want to know A inverse also belong to the center, right? So let us start with, since A belongs to the center for and given any element G, AG is GA. This is exactly the earlier case. Multiply by G inverse on both sides, G inverse AG, that is G inverse G into A, associated etc. used. Therefore, it is identity times A, which is A, right? Now what do? I want to get rid of this G, so multiply by G inverse. Therefore, G inverse A, G into G inverse, this is A into, I am multiplying by right side. Therefore, A into G inverse, you understand? But this is what? G inverse A times identity, that is G inverse A equal to A G inverse. That means A commutes with, oh, I wanted to say A inverse commutes with. Oh, okay, sorry. That's very easy. Okay, sorry. It's good that I revisited. So let AG equal to GA is given, right? Fix G, take any arbitrary element, then I know this. Take the inverse, AG inverse, this is G A inverse. But this is G inverse A inverse, this is A inverse G inverse, right? You understand? Right. Okay. Now what do? See, as G varies over G inverse also varies over G. That's our argument you give. So I want to know, let us see. Let G in G be given. Let H equal to G inverse, right? Now what do I know? I know AH equal to HA, right? Take the inverse, that is AH inverse equal to HA inverse. But this is H inverse A inverse, this is A inverse H inverse. But what is H? H is G inverse. Therefore, what is H inverse? G. Therefore, G A inverse equal to A inverse G. That means A inverse commutes with each and every group element G. Therefore, A inverse belong to H. A belong to ZG implies A inverse belong to ZG. Good. Okay. I goofed a bit, but I recovered. Okay. You can see that. Right. That these are the few abstract examples also we've given. Please go through it. We have concrete examples and some examples in which in the concrete thing also we should know what you have to check. Okay. What does it mean to say something belong to H? We have to understand. If you had attended foundation course, it would have been easier. The third is purely abstract. Okay. If there is a variety of examples, please go through all of them. Okay. We will continue with the study of subgroups later. Okay. Stay tuned. Take care. Stay safe.